Welcome to NGINX Sprint 3.0, and this session is titled Guide to Adopting Kubernetes. I am your speaker for this session. My name is Rey Lejano. A little bit more about myself. I am a Kubernetes Field Engineer with the Center of Excellence with SUSE by way of Rancher Labs. I'm also an upstream Kubernetes contributor. I was the Kubernetes 1.23 release lead. I'm also the current 1.25 Emeritus Advisor, which is scheduled to be released on August 23rd. I'm also a co-chair for one of the 24 special interest groups. I'm the co-chair for SIG-Docs, which maintains the Kubernetes.io website and also reference documentation as well. I'm also a sub-project lead for SIG Security. This talk is going to cover adopting Kubernetes, but before we talk about adopting Kubernetes, we need to first find cloud-native applications and cloud-native. Next, after that, we'll talk about adopting Kubernetes. Then we'll go into how do we optimize our processes and what tools can we use to optimize. So that's the last session of the agenda, and that's more than pods. First, let's talk about cloud-native applications. First, let's define what cloud-native is. The Cloud Native Computing Foundation defines cloud native as cloud native technologies empower organizations to build and run scalable applications in modern dynamic environments such as public, private, and hybrid clouds. They often involve using containers, service meshes, microservices, immutable infrastructure, and declarative APIs. So cloud native applications are microservice oriented. Microservices, so each meaning that the application is decomposed into separate discrete microservices, which we'll talk about in a little bit here. Cloud native applications are containerized. They are containerized in container images. Each service is packaged within its own container with all of its source code and any dependency. Those containers are dynamically orchestrated. So containers are dynamically orchestrated so we could optimize the resource utilization and to maximize automation as well. Cloud native often uses open source technologies and software. They're often combined with infrastructure as a service, with the hyperscalers, platform as a service, and software as a service services to run these cloud native applications. The key motivations that enterprises might have to adopt cloud native applications or cloud native is one is the speed of innovation. We could innovate much faster using the cloud native concepts. We could scale much faster as well. And we could take advantage of the commoditized infrastructure by those cloud hyperscalers. Lastly, we could also visualize the vision of Agile. So with Agile, we don't focus on the operating system anymore. We focus on building, deploying, updating reliable applications. Let's take a look at a monolith application versus a cloud native application. With the monolith application, it's common to have a three-tier application where we have a presentation layer, application layer with all the core logic and all the application modules, and a data layer as well. Versus the cloud native application approach, which uses microservice architecture, which is an architectural pattern to build distributed software systems. Microservices communicate over networks with the REST APIs, and they're often aligned with business services. So microservices are self-contained in containers. They're lightweight, as most container images are, except for Windows container images. They're crisply defined. They usually have a single function, and they can be deployed atomically. Some other attributes of microservices as well. They're usually polyglot friendly. So one microservice doesn't really care what language the next microservice is using. It's all about honoring those contracts with the REST API. Microservices can be updated in their own release schedule as well. So since they are atomically deployable, they could also be atomically updated or replaced as well. Since all we care about is honoring those contracts from the REST API. They're also loosely coupled, and like I mentioned before, the only coupling that they might have is just honoring those contracts and honoring that REST API. So migrating to cloud native is very difficult, and enterprises should have a strategy for the cloud migration. Back in 2011, I know it's a long time ago, Gartner released their 5 R's of cloud rationalization. These are topics to discuss and to make key decisions on how your cloud migration strategy looks like. So with the 5 R's of cloud rationalization, an enterprise must think about, should they just rehost their application? This is the lift and shift method, where we take our monolith application and we just containerize it. We don't do any optimizations. We just put it in a container image and make sure that it can be run so it has to be verified that all the dependencies are in the container image, and we simply just run that container in the cloud. The second consideration is refactoring. So refactoring, do we refactor the application to be more cloud native, or to better align with cloud native concepts and to better utilize those cloud native environment as well? So this might include like refactoring some part of the application source code itself to take advantage of those cloud native functions and to be more flexible as well. You might also switch to a platform as a service model. Refactoring is more intensive than rehosting, of course, but there are bigger benefits. So it'll be more optimized. You could reuse languages. You could reuse containers. You could also reuse frameworks as well. The third consideration is re-architecting. So sometimes you have applications that are obsolete and they're not compatible with a cloud native with the cloud. So you have to re-architect your application. You might have to divide up your application into individual components, which are microservices, and you rebuild those components as microservices, which then can be individually transferred and migrated to the cloud. But there's more time involved with re-architecting versus refactoring versus rehosting. Then, of course, there's rebuilding. So we could redesign the application to be totally optimized to use in the cloud as well. Lastly, there is replacing. So in case your application is either cannot be lift and shifted or rehosted into the cloud, or it might take too much time and effort to refactor or to re-architect or to rebuild. And if there's an option for a software as a service replacement that you might utilize. So replacing is also one of the considerations. So to summarize, these are considerations that Gartner identified back in 2011 for organizations to strategize on for their cloud migration. All right, the next section is adopting Kubernetes. Adopting Kubernetes is more than just creating Kubernetes clusters and running your containers. There's a lot more complexities with adopting Kubernetes. Even before you actually decide to adopt a Kubernetes, there are some prereqs that are involved. So one of the prerequisites before adopting Kubernetes is adopting containers. So you need to containerize your application, which involves including all your application code and all your application dependencies into a container image. A container is simply is a running instance of that container image. It's portable, so we built all the application with all of its dependencies once, and now we could deploy it anywhere. With that container or with that container image, it always provides us a clean, isolated runtime environment whenever we start a new container. Containers are also meant to be ephemeral. So whenever there's an issue with a container, we simply just replace that container. And when we replace that container, it always gives us that same identical clean runtime environment. So managing a few containers is pretty easy. We know exactly what virtual machines they might be running on. We might know what ports they're exposing, what versions of the container image they're running. So it's pretty simple to manage. Then we get into some real complexity when we run multiple containers, hundreds or thousands of containers. How do we address that complexity? And other considerations like networking. Like when one container exposes a port, how do you make sure there's no port conflicts if there's another container that wants to expose that same port? How do we address security? How do we allow a container access to specific file system? One common example I use, if you run Jenkins, if you want Jenkins access to your host's docker.sock to run containers, how do you allow the access for that container? How do you schedule containers? How do you run containers in US East 1? How do you make sure Windows containers run on Windows worker nodes? What if a container needs a GPU? How do you make sure that a container is scheduled or runs on a virtual machine with a GPU? And how do we automate this? How do we do this at scale? The answer to that is Kubernetes, which has become the de facto standard container orchestrator. There's been a few several container orchestrators before in the past, or currently as well. There's Docker Swarm, there's Mesos, even Rancher had its own. Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services. It facilitates both declarative configuration and automation. Kubernetes is based on Google's Borg container orchestrator, which is what Google used in production for many years. The name Kubernetes itself is Greek in origin. It means helmsman or pilot. And Google open sourced Kubernetes back in 2014. So one of the key benefits for Kubernetes is declarative syntax or declarative configuration, where we state in code what the state of the resources we want to run in Kubernetes. Then Kubernetes works so that the actual state matches that desired state. We don't tell Kubernetes what to do. We tell Kubernetes what the desired outcome should be. And we trust that Kubernetes and all of its controllers will drive the cluster configuration to match that desired state. In contrast to imperative configuration. In imperative configuration is where we would instruct Kubernetes what to do. We say, Kubernetes, run a container, expose this port. So instead of telling Kubernetes to run a container with declarative configuration, we tell Kubernetes there shall be a container running with an exposed port. So Kubernetes drives the actual state to the desired state. And one analogy I like to use is that it's your thermostats in your home and the actual temperature in your home. So the actual temperature in your home is the actual state of your home. The setting you place or you set your thermostat to be is that desired state. You have controllers in your home, which is your HVAC system, your heating system, your AC unit. Once it takes that setting in a thermostat, and it will start the heating or start the AC unit to make sure or to drive that the desired state in the thermostat to the actual state, which is the temperature of your home. Some other benefits of Kubernetes is that it's self-healing. Kubernetes restarts containers that fail, or it just replaces those containers. So like I mentioned before, that containers are meant to be ephemeral. So Kubernetes has health checks that users can define. And if a container has any issues, either starting or it fails a health check, Kubernetes will restart those containers or replace those containers. Another key benefit is service discovery and load balancing. So Kubernetes can expose a port using a DNS name or using the virtual IP or IP address of a node of a cluster itself. And if there's a traffic is very high to a single pod or container, Kubernetes can load balance and distribute that traffic to other pods of your application workload. Kubernetes can also automate rollout and rollbacks. So we could change the desired state of our deployments of our application. And then Kubernetes takes that change of that desired state and it changes the actual state at a controlled rate. So deploying your application on Kubernetes involves just creating Kubernetes resources, like you create a namespace, you create the workload for your application, which might be a deployment, might be pods. You might set up storage with volumes and a claim for that storage with a persistent volume claim. But that's not enough. You need to do more than just create Kubernetes resources. You need to optimize your Kubernetes cluster and your workloads using processes and tools. So the next section here is called More Than Pods. So we're going to talk about the day 2 processes and tools that's going to help optimize your Kubernetes adoption, also help it maintain it as well. and also make it more secure. So the first topic is infrastructure as code, which is declarative management of your virtual machines and your Kubernetes clusters. And with infrastructure as code, you automate our infrastructure management. So we're making our infrastructure a repeatable and predictable process as well. So automating infrastructure includes lowering the potential for any human error when we deploy and manage that infrastructure, those VMs, those clusters. We take the same template, and we could use that same template multiple times to create identical environments. So we're creating identical virtual machines. We're creating identical Kubernetes clusters that our organization can use. We also reduce the cost of development and test environments by only having them or creating them on demand when we need them. Some tools like Terraform, we could actually understand the infrastructure changes before we actually apply them. So as your infrastructure topology becomes very complex, we could understand the impact of possible infrastructure changes before they actually take place. So tools like Terraform, we could actually validate and preview the infrastructure changes before applying that Terraform plan. So we could preview those infrastructure changes in a safe way, so we could catch any unintended changes before they actually go live into production. Next process that is great to use to adopt with Kubernetes is a CI/CD workflow with GitOps. So first, let's talk about the continuous integration, which is and do want to make a note that everyone's CI/CD workflow and pipelines are different. This is just one example, and some organizations might have a different definition, might include different steps in their CI and in their CD as well. Or some organizations may not use GitOps or Git repository, but GitOps is on the fast rise for adoption by organizations using the cloud-native approach. First, let's talk about the continuous integration pipeline. So this is where an example of this, in this case, I'm going to walk through example a little bit as well, as where we run the pull request pipeline steps. We do any testing, we do integration tests, we could do unit tests as well. We can make sure that the change that a developer has made is okay to merge. And once it's merged, we could trigger a build an artifact of your application with those changes from a developer. With the CD pipeline or the continuous delivery pipeline, it could be automatically triggered by an artifact that has been built by the CI pipeline. So we could use the artifact, or it could be triggered by, let's say, a new updated container image in your container registry. And that's the artifact that triggers a CD build in this example. With your continuous delivery, once it is triggered, it could set up any environment values or variables that your cluster or that application might use. Then it could also open a pull request to a second Git repository, and this Git repository holds the manifest for your Kubernetes resources. So it's going to change. So with this pull request, once it's merged, it will change the desired state of your Kubernetes cluster. Once that is merged, there's usually a GitOps tool involved, like the common ones are Argo, Fleet, and Flux, and there's more out there as well. Those tools, they will be triggered with the change in the Git repository that holds the Kubernetes resources. So in this example here, starting with the change code, we have a developer that is updating an application that is going to make their commit to the Git repository that hosts the application source code. So in this first step, that developer is changing code, makes a commit, makes a pull request to the application source Git repository. After this, the pull request might trigger the CI or the continuous integration pipeline. So it's going to run its tests to make sure that the changes in that pull request and that change in the application source code is valid and will successfully pass any unit tests or integration tests as well. Once it passes tests, it could create the build. It will build an artifact for that change. So in this case, let's say it's updated container image. So the build process is just creating a container image with the updated code. That container image is then pushed into a container image registry. And there's common ones out there is Docker Hub, there's Harbor, there's Artifactory, there's Quay. You could also use your own private Docker registry as well. And there's also a private Docker Hub as well. So the build process will include creating that container image and pushing it to a container image registry. Once the artifact is at that registry, it might trigger a continuous delivery pipeline, in which case the CD build picks up the artifact, in this case, that new updated container image. Then it will make changes and open a pull request to another Git repository that now is a source of truth for the state of the Kubernetes cluster or the state of the applications as Kubernetes resources. So in this case, the change that new container image that is now in the registry, that triggers a CD build, which now triggers a pull request to the Git repository, which houses the cluster's desired state. Once that pull request is merged, a GitOps tool like Argo, Flux, or Fleet will see that there's a change in that Git repository and will apply the changes to your Kubernetes clusters. So in this way, we automate our deployment workflow as part using GitOps, so using Git as a single source of truth. So part of day 2 operations is security. And with the use of containers and Kubernetes on the rise, there has been a challenge with traditional security tools. Traditional security tools don't work well in cloud-native environments. There's many reasons. One of the common reasons is that Kubernetes obfuscates network traffic. So like with traditional data centers or with traditional security, the best approach is always a layered security approach, which is defense in depth. So where we have multiple layers of security, so at any point, it could be at the ingress, it could be expansion, it could be connection, it could be downloading exploited packages or downloading an exploited container image. We could make a stop at any point. We could detect those vulnerabilities and prevent those vulnerabilities from actually taking place in production. So in this diagram here, we are approaching Kubernetes security in multiple layers. First layer is the supply chain side. So how do we prevent bad stuff from getting into our pipeline and getting into production? So with supply chain security, we want to run vulnerability scanning, CVE scanning, throughout the software development lifecycle. As soon as a container image is created, we want that container image scanned. This also and we can also do compliance scanning and reporting as well against compliance frameworks like GDPR, HIPAA, NIST, PCI, SOC 2. Mission control could also be part of runtime security as well. So mission control, which we'll talk about in the next slide, is a final gate between your pipeline and production. Then we have runtime security. So on the runtime side, we are protecting our containers and the runtime environment in production. With runtime security and specifically with zero trust controls, we know what our application is doing or should do. Anything outside of that, we want to stop and we want to prevent. So we can do that with mission control, which is policy and governance. So in mission control is validation. But in Kubernetes, there are third-party mission controllers that are available that can intercept requests to the Kubernetes API and could validate those requests and could also change those requests as well to satisfy policies. So with third-party mission controllers like NuVector, OPA or OPA Gatekeeper, Kubewarden, or Kyverno, and there's more out there as well, these third-party mission controllers will take that request to the Kubernetes API, will make sure it's been authenticated, authorized correctly, and it'll validate it against existing security policies. And it could also change those requests as well. So it can mutate those changes. Some very common policies are that all container images must be from your allowed container registries. So if your organization probably has your own container registry, it could be internal, be hosted out in the cloud, and a mission controller will make sure that all your container images must come from your organization's allowed container registries or private container registries. A second common policy is that all pods or all containers in a pod must have resource requests and limits for CPU and memory. So a common thing I've seen in clusters is that a single container will use all the CPU or memory of the cluster. And you can limit that by setting CPU and memory resource requests and limits. And a common strategy as well is that if your resource request to the Kubernetes API does not include setting CPU and memory resource requests and limits, the third-party admission controller will mutate that request and add in assigned CPU and memory resource requests and limits. Finally, a third common example of a policy is that a namespace, which namespace in Kubernetes is used to separate out objects, must have the proper labels. So a namespace must have a label to identify who owns that namespace, who owns those objects in that namespace. So it might require, so you might have a policy that will have a label for the team or the business unit that owns that namespace and owns the objects in that namespace. And like I mentioned before, there's tools out there like NuVector, OPA Gatekeeper, Keyboard, and Kyverna. And to summarize all the tools that we reviewed for infrastructure as code, we have some examples are Terraform, Ansible, Chef, and Pulumi. For CI/CD, Jenkins is still very common in Jenkins X. There's also GitLab CI, which is increasing, Circle CI, Bamboo, Travis. For GitOps tools, there's Argo, which is currently leading. There's also Fleet, which is a project from SUSE and initially from Racher Labs. There's also Flex as well. For security and mission control, there's NuVector, and there's OPA Gatekeeper or OPA Gatekeeper. There's also Keyboard and Kyverna. To summarize what these tools do, and to summarize what these tools do and these processes do to help optimize our Kubernetes or cloud native approach, is that we are applying everything as a code, which is kind of a newer concept, is where we have infrastructure as code, we have our application as code, of course. We're using GitOps because Git is the single source of truth for our application and also for a Kubernetes cluster, might be also for infrastructure as well. We could also, and then with security and mission control, security policies or mission control policies are common written in manifest. So that's your security as code. So I want to thank you for attending this session. Have a good rest of your NGINX Sprint 3.0. Thank you very much.